Hey everyone, and welcome to this explainer, brought to you by Forge College. I am absolutely thrilled to guide you through today's topic. Now, if you were with us for the previous lesson in our EVM to SVM track, you'll remember we spent a ton of time down in the trenches, auditing and debugging Vault implementations. We were validating invariants, making sure total supply equaled the sum of balances, and hunting down those tricky cross-account state transition bugs. But, during that whole process, we kind of hit a wall. We realized that for any operations involving transferring or burning tokens, external approvals were the missing piece of the puzzle. So today, we're taking that aha moment and bridging it to our lesson. Permit-based approvals on Solana, motivation, and EIP-2612 comparison. We're going to map out exactly why gasless approvals are a game changer and compare how Ethereum's EIP-2612 model translates to Solana's completely unique architecture. Let's get into it.
Okay, let's quickly look at our roadmap for today. First, we'll cover the gasless approval dream, then the power of attorney concept, followed by EIP-2612 on Ethereum. After that, we'll look at the Solana translation, designing for security, and wrap up with next steps and takeaways.
Section 1. The gasless approval dream. Why pay just to say yes?
I really want you to ask yourself, why on earth do we force users to pay gas just for a simple approval? Think about traditional blockchain interactions. If a vault requires you to grant an allowance before you can deposit or borrow, you have to submit a whole separate on-chain transaction. You have to hold the native gas token, manage two different operations, and on top of that, you're exposed to front-running between the approval and the actual use. Honestly, it's literally like walking up to a toll booth and having to pay a fee just for the privilege of handing the operator your own wallet. It is a total UX nightmare. Permit-based flows completely fix this by decoupling your intent from the actual transaction submission. Basically, you say yes off-chain, and someone else pays the toll.
All right, moving to Section 2, the power of attorney, the core mental model.
To really grasp this, we need a foundational mental model that applies to absolutely any blockchain, and that's the concept of a permit. A permit is essentially a sealed, time-stamped power of attorney. In the real world, a power of attorney has your signature, a specific date, and gives someone else the legal right to act on your behalf, right? Well, in Web3, you can visualize a permit as a sealed envelope. Inside this envelope is your strict intent, exactly who can spend your tokens and precisely how much. Securing that envelope is your cryptographic signature, and stamped right on the outside, a strict deadline or block height window.
So this life cycle breaks down into three distinct roles. First up, you have the grantor. That's you, the owner, signing that sealed envelope offline for free. Second is the grantee, or the relayer. They take your envelope and are the ones actually paying the gas to post it on-chain. Finally, we have the adjudicator. I always like to picture the adjudicator as this incredibly pedantic, strictly by the book on-chain clerk. This clerk inspects your envelope, and if the signature doesn't perfectly match the owner, or if the deadline has passed by even a single second, the clerk refuses to open it. Boom, access denied.
Section 3. EIP-2612 on Ethereum, the EVM baseline.
Now that we have our highly pedantic clerk in mind, it's pretty fascinating to see how we map that exact clerk to the Ethereum virtual machine using the EIP-2612 standard. The EVM clerk relies on three essential building blocks to make sure your envelope hasn't been tampered with. First, EIP-712 typed structured data hashing. This guarantees the clerk can mathematically reconstruct exactly what you signed. Second, the domain separator. You can think of this like a wax seal that explicitly binds your signature to a specific token contract and a specific chain, so nobody can pull a fast one and reuse your signature on a completely different network. And third, a per-owner nonce. This is just a unique number that ensures your envelope can only ever be opened exactly once, totally preventing any replay attacks.
Now here's the really crucial point. On Ethereum, the token contract manages this per-owner nonce storage seamlessly. Because the EVM uses a single contract storage model, when the clerk accepts your permit, the contract just increments your nonce internally during the exact same transaction that updates your allowance. It's incredibly efficient, and it makes replay protection super straightforward.
Section 4. The Solana translation, bridging to the SVM.
But here comes the twist. When we cross over to Solana, everything we just talked about changes structurally. As you can see, we're moving from Ethereum's SecP256K1 signatures using eRecover straight over to Solana's ED25519 signatures, which rely on syscalls or transaction pre-approvals. We also don't have that simple internal token contract storage anymore. On Solana, we have to actively decide where this state lives. Is it a program-derived address, the vault state itself, Or is it bound directly to the transaction? Plus, instead of a standard EIP-2612 domain separator, Solana requires an explicit payload ID right inside the message. It's a whole different ballgame.
The big takeaway here is that Solana's runtime model is entirely centered on explicit account access. Instead of just firing off a simple internal contract call like on Ethereum, Solana actually forces our pedantic clerk to work a lot harder. You have to explicitly pass the public key and the message to the program, usually through an EIP-2612 verification syscall. You literally have to tell the program exactly which accounts it's going to touch before the transaction even runs.
Section 5. Designing for security. Trade-offs on Solana.
Because the underlying mechanics are so drastically different, we have to make some pretty critical architectural decisions. No matter what, these 3 security goals are absolutely non-negotiable. 1. Strict authorization. The signature must perfectly bind the intent to the owner. 2. Bulletproof replay protection, ensuring the permit can never ever be used twice. And 3. Atomic application. Guys, this last one is huge on Solana. The on-chain verification must happen in the exact same atomic step as the state change. If there's even a tiny gap, what we call a time of check to time of use vulnerability, a malicious relayer could just walk right around your invariant checks and cause catastrophic double spends in your vault.
Because we desperately need that atomicity, you have to carefully choose how to store your replay state. You essentially have 2 main options. On the left, the PDA nonce, or program-derived address. This behaves a lot like Ethereum. It's persistent, offers a great user experience, and increments simply. But it creates new accounts, which means it incurs rent costs on Solana. On the right, we have the transaction-bound nonce. This requires the permit to be consumed in the exact same transaction that verifies the signature. It costs absolutely nothing in persistent storage and guarantees strict atomicity. But the catch is it forces the user or relayer into a really tight single submission constraint.
So how do we solve this trade-off? Well, a lot of times the most pragmatic design choice is what we call the hybrid pattern. You use lightweight PDA nonces for long-lived persistent approvals, where the user really wants that smooth EIP-2612 style sign once, use later experience. But then you also support quick transaction-bound permits for immediate one-off operations to save on those rent costs. It really gives you the best of both worlds, ultimate flexibility while maintaining absolutely rock-solid vault security.
Finally, Section 6. Next steps and takeaways. Preparing for implementation.
We've covered a ton of architectural ground today. But before you go prep for the actual code, I want to leave you with this core philosophy to burn into your memory. Permit separate cryptographic consent from transaction submission. That's the whole magic trick right there. Regardless of whether you're building on Ethereum or Solana, regardless of whether you're using eCreCover or ED25519 syscalls, this is the foundational truth you have to protect. It is all about improving the user experience securely.
Now that you've got this conceptual blueprint down, you are fully prepared to start writing the rest implementation. In our next explainer, we're going to get our hands dirty implementing these exact permit structures and signature verification logic right on Solana. Before you jump in, I highly recommend reviewing the official Solana ED25519 verification syscall documentation. And hey, remember, you can always visit forge.college to dive deeper into this subject and explore a whole wealth of other Web3 educational topics. Forge College is absolutely your go-to resource for mastering these advanced patterns. All right, I'm going to leave you with one final, provocative question to ponder before our next deep dive. Go look at your own Solana program architecture right now. Seriously, go look. Is your vault's replay state truly atomic with its invariant checks? Because if it's not, you just might have a critical vulnerability waiting to be exploited. Think about that, and I'll see you in the next explainer.